explain the variation of parameters, I first have to talk about the Cramer's rule. Right, Cramer's rule. How many of you know Cramer's rule? I guess you haven't seen it. It's not that important, but it's kind of good to know. Okay, so let me explain. All right, Cramer's rule is the following. It's suppose you have ax plus by equals to m, and cx plus dy equals to n. And you have to solve this. One way to solve it is you write it as a matrix form: A, B, C, D, X, Y equals to Mn. So for this, everyone knows, right? And then this will have a unique solution if the determinant of this matrix is non-zero. So let's assume that it's non-zero. Now, if the determinant is non-zero, then there's an inverse of this matrix, right? So you can write the solution as xy is equal to the inverse of this matrix times mn. And we even know the formula for this inverse, hopefully. Do you know the formula for the inverse? It's 1 over AD minus BC, and then what? What goes in here? So D and A switches.
Okay. And then negative.
Yeah, B and C get negated. And this can actually allow us to write the full solution. By the way, this is the determinant of the matrix, so let me write it like this. And this one, if I do across down to do matrix multiplication, it's dm times dm minus bn. And then this one will be negative cm plus an. So that you have x equal to dm minus bn over a, b, c, d. But there's a beautiful way to write this. You look at this top and say, hey, that looks like a determinant as well, right? It's something times something minus something times something. So you think about what it could be, and you realize it's really m, n, and b, d. This is not the only way to express it as a determinant, but this would be one way to do it. And I like this because what's really happening is that it's like taking this determinant form but replacing the first column by m and n. You see what I'm saying? First column. The first column is replaced by this. Right? Okay. And if you look at the y, it's exactly the same thing. The y is negative cm plus an. And this one is again a determinant where your a, c are preserved, and you have m and n here. And as you can see, this time the second column is replaced by m and n. And it's a very beautiful kind of formula. So let's do a quick example. Say you have like 3x plus 4y equals to 2x plus 3y. And let's put 2 and 3 there. Okay? Then what's x? Well, first the denominator will be 3, 4, 2, 3, right? So it's again 3, 4, 2, 3, but the first column is replaced by 2 and 3, right? So it's 3, 4, 2, 3, but the first column instead of 3, 2, you have this, right? And then if you look at this, 3 times 3 is 9. 9 minus 8 is 1, so the denominator is 1. So you just have this. 6 minus 12, so it's negative 6, right? And for the y, we already know that the denominator is 1. And the top one will be, this time, 3 and 2 will be preserved. And 2 and 3 will be replaced here. So 3 times 3 is 9. 9 minus 4 is 5. So you have 5 over 1, which is 5. So you get the value of x as negative 6 and y is 5. So it's pretty neat. That's called the Cramer's rule. Now, this actually is true for 3 by 3 case. So if you have x, y, and z, if you have 3 unknowns, then you're going to have 3 equations. So you're going to have a 3 by 3 matrix. And again, the value of x and y and z will be expressed as ratio of 2 determinants, where the denominator is the determinant of the entire 3 by 3 matrix, and the numerator is just either the first column replaced by the constant column, or the second column should be replaced by this constant column if you're looking for y, and then to find z, you have to replace the third column of the matrix by this one. So that's what Cramer's rule is. It's beautiful, except that we don't teach it much these days because computationally it's not that effective. So if you have some really large matrix and you have to solve it, Cramer's is actually not that efficient. It's actually easier to use Gaussian elimination or some other Gauss-Jordan elimination. There's some other methods out there that are faster, so it's less used. However, I still want to mention this because if you look at the formula for this thing called variation of parameters, this does come up later, okay? So, yeah, you have a question?
So that's like when you're trying to find the determinant, like you use Cramer's rule?
No, you use the Cramer's to solve a system
Okay.
using determinant. You're not trying to find the determinant. We're assuming that you know the determinant, and you're trying to use the determinant to solve the system. So look at what I did. I have an equation, and I found the solution using the determinants. Okay? Seemingly easier than actually solving it, right? Okay. All right. So that's Cramer's rule. Now let me get to the core part, which is the variation of parameters. So what is this variation of parameters? Variation of parameters is a way to find the particular solution, assuming that you know the complementary solution. So let's say you have a second order differential equation, y double prime plus ay prime plus by equals to f of x. And there are a few things that I could have some constant in front, but then even if you have something in front, you can just divide by it so that always the y double prime has just 1. So this is quite general. But additionally, I wrote a and b as if these are constants, just so that our calculation is easier. But everything I say will still be okay, even if a and b are actually functions of x. Okay? So, it's quite general. Okay? So suppose you're given this differential equation and you want to solve it. And always step 1 is to find the complementary solution, right? So let's say your complementary solution, yc, is like c1y1 plus c2y2. Okay. And for those who don't yet quite understand what complementary solution means, it means that individually these give you 0 on the right side. So individually, if you have y1 plugged in, if you plug this on y1 on the left side, you get 0. And that's what it means. Okay? And same thing for y2. Okay, so let's say these are the given. Then with this given, here is what I want to say. The variation of parameters is an idea to find a particular solution. And it's the same kind of reasoning that I've been telling you throughout the semester. We don't solve differential equations. We make guesses. We make educated guesses. And often that educated guess means it's not a total shot in the dark. Rather, you cook up some form of the solution that seems likely or possibly be able to be a solution of this. So you come up with an ansatz, right? That was a deal, right? And the ansatz for the variation of parameters is you take the complementary solution, and what you do is, these are coparameters, right? C1 is a parameter, C2 is a parameter. You take those and you promote it to a function of x. So what you do is you write u1, y1, plus u2, y2. And here, really, even if I did not write it, I'm really saying that yp is a function of x, u1 is a function of x, y1 is a function of x, u2 is a function of x, y2 is a function of x. But then that looks too long, so I don't want to write it like that. But you see what I mean, right? Okay. So that's what I want. Okay. So that's my suggestion. This should be a solution to this. Okay. So how do you? So you have an ansatz. How do you get the actual solution from an ansatz? You plug it in and make it work, right? That's how you do it. So what we're going to do is we're going to take this, differentiate once and twice, and plug it into the left side. Okay, so let's do that. So we're going to differentiate once. Okay, let's see if you're following. What will be the derivative of u1, y1?
u1 prime, y1 plus u1, y1 prime.
Thank you. What are we doing here?
Product
rule. Yeah. And then so same thing applies here. u2 prime y2 plus u2 y2 prime. Those are what we get. Okay. Now already you are hesitant to go the next step, because if you differentiate this again, then you're going to get 8 terms. Some of them might be the same, so you can combine like terms, but still it's just too complicated. So you want to stop right here and think about what else you can do. Well, here's another thought. So, sometimes being lazy helps, okay? Yeah. So if you're too hardworking, you don't see it properly. So if you stop for a minute and think about what you're doing, it helps. So let's say we did do the work. Okay? Yeah. Rather than doing the work, imagine doing the work. That's another way to do the work. Okay? So differentiate, and let's say we plug it on the left side. I have things to plug in here, plug in here, plug in here, and it should be equal to f of x. Okay. Now, in the given, we already know the y1, we already know the y2. So we just have to figure out what u1 and u2 are. So we have two unknowns, two unknown functions, u1 and u2. Suppose you did the derivative, did the second derivative, you plug in the left side, and you say equal to the right side. How many equations are you going to get? Plug this in, plug that in, plug this one, equal to f of x. How many equations is that? Just one. You just have one equality, right? Now, is that good?
No.
Why not?
You need multiple.
You have two unknowns, so how many equations do you need? You need two, right? You need two. So already you know that this is a futile direction. However, change the perspective. Think of it like this, okay? I have two freedom. U1 and U2 can be anything. Freedom, right? But then once you put the second derivative, first derivative, and itself to the left side and set equal to the right side, there's one restriction. Okay? So we still have one more restriction we can give, right? Because with two restrictions, then U1 and U2 will be determined, right? If you take that perspective, then you say, okay, so I like that. I'm going to say that I'm just going to impose another restriction, okay? So that with the two restriction, then U1 and U2 can be defined. In other words, I have an allowance for one extra restriction I can give. Does that make sense? Okay. And that restriction that I'm going to give is to suggest that this one plus this one would equal to 0. Okay, so let me write that down here. I want to say U1 prime Y1 plus U2 prime Y2 has to equal to 0. That'll be my first restriction. Okay? And that means I can happily say that these two can't, this plus this goes away, right? This plus this goes away, and now we have these two. And then I can happily do the derivative. Okay, so you have U1, again, if you differentiate, you have to use the product rule, so it would be U1 prime Y1 prime plus U1 times Y1 double prime plus U2 prime Y2 prime plus U2 times Y2 double prime. Okay, so now we plug in everything on the left side. Let's see what happens. We have this one by itself, so U1 prime Y1 prime plus U1 Y1 double prime plus U2 prime Y2 prime plus U2 times Y2 double prime plus, and then there's an A times this thing here, U1 Y1 prime plus U2 Y2 prime plus B times U1 Y1 plus U2 Y2 equal to 0. Okay. And then I'm going to organize it so that first I want to bring the U1 prime Y1 prime. Oh, sorry. Should it equal to 0? What should this equal to?
FX.
Fx, right? Okay. Sorry about that. Okay. So we have U1 Y1 prime plus U2 prime Y2 prime. So set this apart. And then I want to organize so that U1 times something plus U2 times something equals to f of x. So I want to organize things so that some terms that have U1, I factor the U1 out. Some terms I have U2, I factor that out as well. Okay, so let's hunt down the terms with U1. I see U1 here. That's the very first one, right? What's the next one? The second line right here, right? What's the next one? And this one. So those three. So if you take those three, add them up, and factor the U1 out, you end up with Y1 double prime plus A Y1 prime plus BY1. And if you do the same thing, you'll see that the second one looks very similar, except that it's instead of 1, you have 2. Okay, tell me what this is equal to. What's this equal to, this one? Huh?
F of x.
Not f of x. It's equal to?
0.
0, right? I said it right here. It's equal to 0. Because it's a complementary solution. Complementary solutions, those are the ones that give you 0, okay? That's important to know, okay? Complementary solutions are the solutions where the right side is replaced by 0. So that one's just 0. And the same thing here. This will also be 0. So you end up with the result, which is that this should be equal to f of x. So let me write it here. U1 prime, Y1 prime, plus U2 prime, Y2 prime equals to f of x. Okay. So that's what I get. And that's fantastic because we have two unknowns, U1 and U2, and you have two equations. So that should mean that we can solve for U1 and U2. Okay, now let's rewrite that equation as a matrix form because I talked about the Cramer's rule, so I want to use it. So let's see. I have the well here. It's the important thing is that U1 prime and U2 prime are the ones that we do not know, so those go here. Yeah, it's hard if all of them are just letters. It's hard to see which one is out of the given and which ones you're trying to solve for. Here, y1 and y2 are considered as given. So it's y1, y2 goes here, y1, y2. And then in the next line, it's y1 prime, y2 prime. On the right side, equal to, what goes here and here?
0 f of x.
0 and f of x. Okay. And now we can use the Cramer's rule. Right? We can use the Cramer's rule. So let's see if you remember it. U1 prime is equal to what over what? So first, the denominator, what goes here? y1, y2, y1 prime, y2 prime. Okay? And what about the top?
Is it y1?
0 fx will replace the first column,
Yeah.
and then y2, y2 prime. Okay. Now, I want to simplify this because I have a name for this. What is this thing called? I wonder if you remember. Not well. It's a determinant, but it's a matrix determinant, but it has a special name. If you have two functions and you put the derivative to make a square matrix and you take the determinant, that's called a.
It starts with a K.
Starts with W.
Oh.
WR.
Wronskian?
Wronskian, yes. Good. Okay, so what does Wronskians do?
There's a K in it.
What do you use it for, though? Alright, what do you use it for? If you want to know whether two given functions are linearly independent,
See, it sounds like a plus.
you take the Wronskian of it, and it has to be non-zero, okay? If the Wronskian is non-zero, then the two functions are linearly independent.
Great.
And actually it's true because if you have the complementary solution like this, if you're able to write it this way, you're assuming that y1 and y2 are linearly independent, or else it doesn't give you the full solution, right? That's why we talked about in the beginning of the semester, right? So because I know that the complementary solutions are given like this, of course y1 and y2 will be linearly independent, so of course this will be non-zero, which is a good thing because denominator shouldn't be 0. So for this one, I'll just use W for it, the Wronskian, W. Okay? And W just means this. Okay? All right, what about this determinant? What do you get if you do AD minus BC? Negative
f of x, y2.
F of x, y2. Okay? And if you write the same thing for U2 prime, the denominator will still be W, but the top one will be y1 and y1 prime will be still here. And what do you put over here? What goes here and there?
0.
0 and f of x, right? So if you do AD minus BC, this will be f of x times y1 over W. Okay, so we're almost there. What do you mean almost there? It looks like we obtained something, but this is not the answer yet, right? Because we're going for the particular. Okay? This is our ultimate goal. So we have to get U1 and U2. So how do you get the U1 itself? What should you do?
Can you do the integral?
Yeah, because this is derivative, you have to integrate. Okay. So it'll be integration of negative f of x, y, 1x, and w of x, dx.
Would be y2.
Oh, thank you, it's y2. And I'm putting x's back in just so that it's clear to you that all of these could be functions of x. Of course, sometimes they might be constant, but in general they could be functions of x. And then u2 would be integral of f of x times y1x over wx dx. Is that the answer? Not yet, because we were looking for yp, right? So what's the final answer? Yp is y1 times u1, which is this one,
Y2.
plus y2 times the integral of f of x y1x over w of x dx. Okay, so that's the formula for the that's the formula for the particular. And just to give you a quick idea of how you can use this, so here's a quick example. So say you have y double prime plus y equals to 1. The simplest thing I can come up with. The complementary solution is c1 cosine of x plus c2 sine of x. So if you do cosine double prime plus cosine, you get 0. Same with sine, right? So if you calculate the Wronskian, okay, let's see if you can calculate the Wronskian. What did I put here on the top? Cosine x and then sine x, right? What next? You keep differentiating until you get a square matrix, okay? So cosine differentiates to negative sine x. Sine differentiates to cosine x. Okay. And then what do you get?
1.
Yeah, it says cosine squared of x plus sine squared of x, which is 1. That's why I prefer this example. I tried something else yesterday in a different section and it didn't work out. So let's do the one that's easiest, okay? And so now you have a very easy way to do things. So yp would be y1 is cosine x times the integral of negative 1 times y2x, which is sine of x, over 1 dx, plus sine of x, positive 1, cosine x, over 1 dx. Right? And sine integrates to negative cosine, so you end up with negative of negative cosine, which is positive cosine, so you get cosine squared of x. Same thing here, cosine integrates to sine of x, so you get sine squared of x. So you get 1. Oh, and by the way, there's something I should have said. Although our initial goal was to just to find the particular, if you actually write the solution as cosine x plus c1 and sine x times sine x plus c2, notice that I have to say c1 and c2 because they don't have to be the same constant. But if you do that, you see that cosine squared plus sine squared gives you 1, and you still have c1 cosine of x plus c2 sine of x. So you get the full solution, not just the particular solution. You get the solution of this equation in general. So if you plug this in, you see that it will satisfy this differential equation for any parameter c1 and c2, and because it has 2 free parameters, you know that this is the entire solution. Okay. Wait. There's one more thing I have to add, which is actually quite deep. So here's what I want to say. If you replace the x's by t, put this as t, same thing here. Now this itself is no good because you need a function of y as a function of x. So what I want to do is I want to integrate this as from 0 to x. 0 to x. Okay. Then if you integrate and you plug in x and 0, you do get a function of x, right? Okay. And this is a function of x, right? Y. And now what I can do is I can rewrite this as yp equals to integration from 0 to x of one of them will be negative ft y1x y2t. And the denominator will be same as wt. And then you have plus f of t, y1 of t, y2 of x, dt. And you can even factor this f of t out. So you can put the f of t outside. And this thing here will be, denominator will be wt, and on the top it will be, let me write this one first, y1t, y2x, minus y1x, y2t, dt. And this thing here, if you name this as g of xt, because it's a function of both x and t, right? Then the solution has this nice form. The solution of this differential equation, so let me go back. Here's our differential equation, y double prime plus ay prime plus by equals to f of x. The solution looks like 0 to x of ft times g of xt dt. And basically you have some function, this is called the kernel of an integral transform, that would just automatically give you the solution. And this one actually satisfies two additional properties you can check. So y of 0 will be 0, and then y prime of 0 will also be 0. And this function has a name. This is called the Green's function of this problem. It's not the same thing as Green's formula, Green's theorem. Green's theorem is a totally different thing. The Green's function, you're going to use this in harder mathematics. This Green's function is like an inversion of this operator on the left side.
Is it similar to like Green's theorem at all?
No, it's totally different. It has nothing to do with Green's theorem. The Green's function will just solve a differential equation for you. So often in harder mathematics, when they solve a differential equation, they just ask for the Green's function. And it satisfies all kinds of different properties, like if you switch x and t, it becomes negative and all that. So it's somewhat interesting. Okay, that's all.